AC circuits. Part 3, the RC circuit.
In the last video, you were introduced to phasor diagrams, which are graphic representations of the peak value and phase angle of AC sine waves.
Based on phasor diagrams, you saw how the Pythagorean theorem can be used to calculate not only the resultant phasor, but the phase angle, theta, as well.
By now in your AC studies, you have a basic idea of how resistors, inductors, and capacitors work when connected individually to an AC source. But in actual circuits, these three devices are used in combination. It's important for you as a technician to be able to analyze the interactions among these components in advanced AC circuits. In this video, circuits that contain both resistors and capacitors, known as RC circuits, will be thoroughly examined.
They will be analyzed in both series and parallel configurations. Two basic types of relationships will be presented as useful guides for analyzing any type of RC circuit. Impedance will be defined and calculated. Finally, you'll see how varying frequencies affect voltage and current within RC circuits.
Before beginning to analyze RC circuits, it's important to realize no matter what combination of resistors and capacitors a circuit may have, that resistors will always respond as resistors and capacitors like capacitors. All of the advanced AC circuit concepts that will be presented in this video are derived from fundamentals that you've already learned. Let's take a look at a series RC circuit.
It consists of a resistor and a capacitor connected in series with an AC voltage source. One important aspect to notice whenever you examine a series circuit is that the current is the same throughout the circuit, according to Kirchhoff's current law. The source current, I sub S, the resistive current, I sub R, and the capacitive current, I sub C, are all equal. They are identical in both magnitude and phase.
Next, there are two types of fundamental relationships that you should keep in mind when working with RC circuits. These relationships will always hold true no matter what configuration of resistors and capacitors you may find. They are phase relationships and Ohm's frequency relationships. To understand these relationships, it's helpful to look at each component separately.
Recall that in an AC circuit, the voltage across a resistor is always in phase with the current through the resistor. Remember, too, that a capacitor's current always leads the voltage across the capacitor by 90 degrees. When the waveforms of these two devices are compared, it becomes clear that since the currents are in phase in a series circuit, then the resistive voltage will lead the capacitive voltage by 90 degrees. This phase relationship is fundamental to understanding how an RC circuit will operate. Because the voltages are out of phase, Kirchhoff's voltage law becomes too cumbersome to use when calculating total voltage, as was demonstrated in the last video. Although each pair of points in the two waves can still be added to find the total voltage, the process is very time-consuming.
Instead, phase relationships can be used for determining the total voltage. Let's see how this is done using what you already know about phasor diagrams and the Pythagorean theorem.
First of all, remember that phasor diagrams can be used to represent multiple voltages that are 90 degrees out of phase. V sub R leads V sub C. If, for example, the voltage drop across the resistor is 4 volts and across the capacitor is 3 volts, then the phasor diagram can be drawn this way. The resultant phasor for total voltage in this circuit can be found by using the Pythagorean theorem. V sub T equals the square root of the quantity V sub R squared plus V sub C squared. Substituting the values yields V sub T equals the square root of 4 squared plus 3 squared, or the square root of 16 plus 9. This becomes the square root of 25, which equals 5 volts AC. the total voltage applied to the components in this RC circuit.
This demonstrates how important phase relationships are when analyzing an RC circuit. Let's consider the second important relationship between ohms and frequency. Again, it's helpful to review each component's characteristics separately at first.
In AC circuits, there is no relationship between resistance, which is an ohm's value, and frequency. Since in an ideal resistor, the value of R doesn't change, then frequency will have no effect on the number of ohms. Let's consider a capacitor. Recall that capacitive reactance, designated X sub C, is the opposition to current flow and is measured in ohms. According to this formula, you know that capacitive reactance is inversely proportional to the frequency. So in every RC circuit, there are two different ohms-frequency relationships: resistance, which is not dependent on frequency, and reactance, which is dependent on frequency.
Before moving on with an RC analysis, it's important to realize that because resistance and reactance are both Ohm's values, they are interchangeable within the context of Ohm's law.
This can be clearly seen if you think of Ohm's law in terms of units. For example, amperes equal volts divided by ohms. Once the capacitive reactance is known in a purely capacitive circuit, the total current can be found using Ohm's law, because current equals voltage divided by capacitive reactance. Let's try an example. Here's a purely capacitive circuit with a 10-volt AC source. At a given frequency, the capacitor has a reactance of 5 kiloohms. Let's find the total current using the new version of Ohm's law. Substitute the values into the equation to get I equals 10 volts divided by 5 kiloohms, yielding a total current of 2 milliamps. What else do you notice about this new version of Ohm's law? By solving for a different variable, you can derive another formula for capacitive reactance. X sub C equals V divided by I.
Let's find the capacitive reactance for an example circuit using this variation of Ohm's law.
This AC circuit consists of a 15-volt source connected to a capacitor. The circuit current is known to be 5 milliamps. From these values, the capacitive reactance of the circuit can be determined. Substitute the values into the formula X sub C equals V divided by I. The formula becomes X sub C equals 15 volts divided by 5 milliamps. 5 milliamps is the same as 5 times 10 to the minus third. This can be rewritten as 15 divided by 5 times 1 over 10 to the minus third. The division yields X sub C equals 3 times 10 to the third, or 3 kiloohms for the capacitive reactance. Stop the program and complete activity number 1. When finished, continue watching the program.